Okay, good morning. Good morning.
Good morning, sir.
All right, let's talk about the P3 deliverable. Don't help. There we go. All right, so there's the actual assignment. You deliver two things. One is submit your software design development document again, but this time it's got the UML inside of it. And we talked about how to produce that over the week. We'll talk a little bit more about that today. And then your first version of the requirements and test document. So you're going to have a set of requirements, a set of tests, and explanatory text ahead of that. The template is here for the requirements and test document. And background information, the main thing there is all your definitions, everything that you need for the requirements to make sense, for the test to make sense. You can even set up scenarios in there, and then in your test plan, you can say, okay, scenario 1, scenario 2, scenario 3. List 5 requirements, tie them to the user stories. Which user stories are you testing? And then each requirement gets 3 test cases. You can have more, obviously. Again, in a real world situation, something of this size, I don't know, you're going to have 30 or 40 requirements, and you're going to have 150, 200 test cases. This is just to give you a feel for how to write these things and how to go through the process. So having said that, let's see. Where do you put your UML diagram? You've already done the introduction and the problem description. You can edit those based on my comments if you wish. I'm working my way through those. You have your user stories. Again, you can edit those or add to those. A lot of people, and you need 12 as a minimum. So far, a lot of people are not turning in 12. And then here under problem solution, that's where you put the UML diagram. Now, don't just plop the figure in there. You should explain what each class is doing. Why is it there? What's its job? You can even explain, if you want, what the attributes and methods are doing. Basically, the one-liner from from the comment block in your code. So you never, and I don't care what you're writing, you never just throw a figure, an image in there or a figure in there or a table without talking about it in the text and explaining to the reader what that image is telling you, what that table is telling you. So that's what's happening in that document. And then lastly, to give you practice, here's homework 4. And so homework 4 gives you a description of the hare and hound game that you're creating. The projectile assignment was the first step in that. Hare and hound is a balloon race where you have a bunch of balloons, and then one balloon goes off and lands somewhere, and then all the other balloons take off, and whoever lands closest to the original one wins the contest. The one that takes off initially is the hare. All the other ones are the hounds. So that's basically what this series of homeworks is going to create. Okay, so this gives you practice in writing requirements, practice in writing test cases, so that you'll get your feedback on this in time for the P3 deliverable. Okay, questions about what's expected in the assignments?
I know for like these homeworks and stuff, it says there's no GUI, but if we want to, can we practice working with a GUI just to get more familiar with it?
You can, and I would recommend against it at this point, but you can. Yeah, if you want.
Thank you, sir.
Basically, if you do include the GUI, you'll be working ahead in the assignments. So if you choose to do that, look at the future assignments, which are posted, so you know what's expected in the GUI. And that way, you know, you won't have to rip apart what you've done and redo it to meet the homework requirements in the future. Yeah, there's nothing wrong with working ahead.
Okay.
Having said that, don't needlessly complicate your life, right? So if you find that you're having trouble turning this in because of the GUI, then you know, don't waste your time with that.
Okay. Thank you, sir.
Okay. I think we talked a little bit about this last week, the requirements and specifications, and looked at some bad requirements and some better requirements. I'm going to come back to this. Let's walk through the process again. So the basic process, you have your overarching vision of the product. You know, that's the P1. Okay, this is the really brief description of what your project is going to do. And then describing the functionality of the product in detail. That's the P2 deliverable that you've done. Getting the detail in there is where people tend to fall down. Someone turned one in that was a machine learning, a neural net machine learning application, had all the descriptions of what the terms of a neural net was, had all the formulas of what a neural net was, how do the nodes get trained, how does this thing use test cases and then iterate. That's exactly what I was looking for. Everything was there, all the formulas were there, all the references and citations were there. You know, that was a really good piece of work, and I'm sure it took that person 4 or 5 hours to do that. Okay, then you create your initial design. We talked about that on Monday and Wednesday. We'll talk about it, go through it again today. Create your requirements and test cases, and then implement your code. And that's what the 4 sprints are for the P4, 5, and 6, and 7 deliverables. So today we're focusing on the initial design and the requirements and test case. And primarily I want to focus on requirements and test cases. So again, here's the cartoonish picture of the sheepdog game. And again, when you're thinking in terms of what your GUI is going to look like, think in these simplistic terms. Creating animations, I mean, real animations where you have characters that appear to be walking or running or throwing. You know, that's kind of beyond the Java basic stuff. When you're going to do that kind of work, you go to other tools. You know, you go to modeling systems like Blender and systems like Unity that were built to create complex graphics. The raw stuff that Java gives you is kind of hard to work with to create really fancy graphics. And that's fine. I've had students turn in really engaging products that I wasted time playing with because they were so cool, that had super simplistic graphics. Someone did a Hooke's law demonstration. You know, springs compression, force in a spring is proportional to its compression. And it was so simple. They had a black rectangle, which was a ledge. They had a black circle, which was a ball. They had an image of a black wavy line, which was the spring. And as you dragged the ball back with your mouse, they just had the size of the image of the spring shrink, and it automatically looked like it was compressing. And then when you let go, it shot the ball off the ledge, and your goal was to try to hit a flag down on the ground below. I mean, talk about simple graphics. And yet it was an engaging experiment. You know, it was an engaging thing to play around with. I mean, black and white, simple shapes, easily done. So think in those terms. Okay, now describing the functionality in detail, we talked about that. Here's your kind of your tests, right? Your tests are, if you took your description and gave it to somebody else where you had no control over how the product was actually going to be coded in Java, then would the thing that came back to you be a reasonable approximation of what you wanted? And The reason that that's a good test is because a lot of people in your head, you have a really good idea of what you want. And then as you're writing it down, you don't actually include a lot of the information that's in your head because of course you know what's in your head, but other people don't. So you're describing what the product does. You're not describing how it does it in the P2. Okay, then we do the initial design, and we talked about this during the week. Okay, you start to say, what classes do I need? And we had a discussion about that during the week. I'll show that slide again. What classes do I need? What attributes does each class have? What methods does each class need? And those are not necessarily trivial questions. Usually getting down to what classes do I need, you can get a really good guess right up front. And then the attributes are not too problematical. It's the methods. What class should do what job? And we use the example of, okay, the sheep need to run away from the dog. Where should that occur? Where should that decision making occur? Where should the determination of the sheep direction and speed, where should that occur? Should it be in the sheep? Should it be in the game controller? Let me put that slide up. Should it be in the sheep class? Should it be in the game controller class? So the answer is there's really no truly wrong answer. Some of them make it harder to modify the program down the line. As a rule, you want the object to be as independent as possible. So as a rule, if the if the sheep are supposed to run away from the dog, you want all that decision making to happen down in the sheep class. But that brings in a brand new problem, which is the sheep doesn't know anything about the dog. So what are we going to do? And we talked about creating a dog attribute in the sheep class and then letting the game controller give access to the memory where the dog data is directly to the sheep. And then the sheep can determine what they should do. I didn't talk about terrain. You see on here, I've got in the sheep class, I've got a dog attribute and a terrain attribute. You make the exact same argument with the terrain. How do the sheep know that they're not running into the fence on the end of the field? You know, the field has boundaries, right? So how do we keep the sheep inside the field of play? And the answer is somebody has to determine if the sheep are running off the edge of the world and stop them. And who should do that? You know, should it be the game controller, or should it be the sheep, or should it be the terrain? And so you go through the same line of arguments, right? There's no best answer. All solutions will work. It's just a matter of how encapsulated are you keeping all your functionality. So in this case, I would say we could make the same argument as we did with sheep running away from the dog. Okay, the sheep have to know, you know, in a real world, sheep would see a fence in front of them, right? In turn, we would hope. And so same trick here. We would have give the sheep the terrain information. And then when the sheep are running up against the edge of the boundary of the game, then they can turn and, you know, have their movement method in such a way that they'll run along the fence line instead of through the fence. And then we get down to requirements and test cases. Now, here's the thing with requirements. These are technically, they're called requirement specifications, and that distinction will tease out when you take SE 300. But I'm using the terms interchangeably here. They're often used interchangeably. Sometimes that's a bad idea. But for now, I'm just calling them requirements. I'm asking you to have 5 of them for your project. Again, that's not a complete requirement set. And then the trick is their scope, their nature needs to be to talk about exactly one aspect of the functionality of the code. And that's what we're calling atomic. They have to be atomic. So one small behavior. If you have the word and, like the program shall do this and that, that's a really strong clue that you've got 2 requirements there. The program shall do this is one requirement. The program shall do that is a second requirement. So that's actually good news, right? Because if you're having trouble coming up with 5 requirements and one of your requirements is the program shall do this and that, The good news is you should break that up, and now you've got 2 requirements. And then unambiguous. And unambiguous, why does it have to be unambiguous? Because we have to ultimately test these requirements. And if it's an ambiguous requirement, then there's no clear pass-fail criteria for the test. You know, again, you should ask yourself always, is this testable? How would this pass? How would this fail? How would I know? And you can't do what we do as human beings, which is, oh, I would know because I'd look at the behavior on the screen and it would do such and such on the screen. That's not testable. Your eyeballs are not calibrated. You test it by looking at data values. So for example, if I had a, sheep cannot go out of bounds. Okay, the lower left, the upper right corner of the field of play is 0, 0. I'm never allowed to have a sheep have a negative X location value or a negative Y location value. So we would have a requirement. Sheep X location must be greater than, shall be greater than 0. So how would you test that? You clearly could try to inject different numbers into the system and see if the method that you use to create movement could ever produce a negative X value. Hard to prove a negative. Right? Now, technically, that would be a let's say the field of play is 600 units long. Then your requirement would be the sheep X location value shall range between 0 and 600 inclusive. That's testable. You can put in different test cases where the sheep are moving along and see if you can force it to go above 600 or force it to go below 0. Or you can actually inject 601 in there and see if you have written a routine that teleports the sheep back onto the field. So we want one small thing, atomic behavior, and then unambiguous testable behavior. And then the other thing that students sometimes have trouble with is this notion of how could I cheat the requirement? That's a really good question to ask. How can I cheat the requirement? And the way that requirements get messed up in is language like if possible. The sheep shall run away from the dog if possible. That sounds reasonable because you're thinking, oh, maybe the sheep's in the corner and can't run away from the dog. So I'm going to say the sheep shall run away from the dog if possible. Well, as a programmer, I have already met that requirement without writing any code because in my opinion, it is never possible. I mean, how easy was that? So working through this, how do I cheat, is a good exercise. And again, for engineers in general, it's always a good idea to ask what could go wrong. We always think about the things that we're designing and building working properly, but all things fail and we need to have a plan for the different failure modes and how to correct them. So, learning to think in terms of what could go wrong, how could people cheat, those are good things to think about. It's a good mindset to get. And then test cases, and we're going to talk again about what that means, specific concrete conditions. I mean numbers. I mean specific values. It's common if I have students who are doing a system that has a login system, let's say. You've got an administrative login, you've got a user login, so you got username, password. And a common test case is put in valid username, password. And then the result of the test should be, system lets you in. Now, why don't I like that test?
Could you repeat the question again, sir?
Oh, sure. So The test case is we're testing the login system, right? The username, password, right? So, and you say for your test case, put in, enter valid username, password. And then the result is, you know, system logs you in, you know, the welcome screen should show up, something like that. Yeah, Milan says it doesn't define what a valid input is. And here's how you know if you have a good test case. Pretend you gave your test case to 10 different people. Would all 10 people perform exactly the same actions? And so if I just said put in a user valid name, put in a valid username and password, and I gave that to 10 different people, they would put in 10 different usernames and passwords, potentially. And that's not a test. Tests have to be repeatable. And the only way you get repeatability is by everybody putting in the exact same value. So a better one is that you create a dummy account for testing. And you say the test cases, enter username, test account, enter password, test account password, whatever you set up for the password for that. And now everybody who performs that test is going to enter the word test account password when they do the test, you know, unless they have, you know, typos like me. So everybody would perform the exact same test because you provided the specific values. And that's the kind of specific things that we want. And we'll talk about how interesting that can be to develop in a few minutes. Okay, 3 test cases per requirement. Yes, you can have a test case that is designed to fail, and your system should notify you that, you know, this is a failed situation. And so that can be part of your expected behavior of the test result, is the system prints out this message. I would always, I strongly encourage you to not so much rely on your test cases on what's happening on the screen. Always try to find an attribute value that has a specific value that you can look at and verify. Because what's happening on the screen is ambiguous. You know, if something was supposed to move 3 pixels and you saw it move on the screen, I defy you to count 3 pixels and verify that that happened. But how did it move 3 pixels? Oh, it's got an X location that had an initial value of 60 and now has a value of 63. Oh, that's verifiable. So try to figure out which attribute values you can look at. Even the one that says for login, the welcome screen should appear. That's great behavior, but why did that welcome screen appear? That's actually the attribute value of one of the GUI objects. So you should have, oh, the attribute value for the GUI object is set to welcome screen. Okay, so once you start implementing the code, you're going to have roughly 12 days each. Oh, I have days here. That's from last semester, so it may be modified a little bit. If we look at our let's see. So you turn in P3 here on March 19th, and then you have until March 29th. So yeah, there's 10 days, and then you have until April 9th. What is that? 9 and 3 is 12 days, and then you have until March 19th. So there's another 10 days. Then you have until May 3rd, so that's 14 days. So you've got these sprints, and again, take for each sprint, take for sprint 1, 10 days long. How many hours do you think you can work on your project during those 10 days? Okay, I think I can work 15 hours on that during 10 days. Okay, take 15 hours worth of user stories, put that in your sprint 1 goals on the Agile tracking sheet. And then sprint 2, okay, I think I can work 12 hours on that. Okay, so grab another 12 hours of user stories, put in there for the second one. Don't do it until the sprint starts though. You only fill out one sprint at a time, the current sprint that you're in on the Agile tracking sheet. Because you don't know what the future sprints look like until this one's done. You may have not completed your work, then that's normal. And so you have to roll that into the next sprint. This slide has something about peer reviews. So starting with P3 and then going through 4, 5, and 6, but not 7, but for 3, 4, 5, and 6, I'm asking you guys to do peer reviews. And what I'm going to do, if I haven't already, is randomly divide you up into groups of 3. And then for sprint 3, I'm going to ask you like 2 days ahead of time to turn in a draft of your report. And then the other 2 people in your group, they're also going to do the same. Everybody looks at everybody else's work. And then make some kind of comment, which is, again, these are improving, think of it as improving the product. So everybody looks at everybody else's work. You do that in the discussion group, and then the hope is that it would improve the product, and you have a good 24 hours left to incorporate the comments. The earlier you want to post your draft, the better off you're going to be in terms of comments. You'll see who's in your group, and so by all means feel free to email them, or if you see them on Discord, remind them to go look at your work. Anything like that, or put in the discussion groups here on Canvas. We get very little student engagement in the online course, right? Very little student-to-student interaction. So here's the one big chance for student-to-student interaction. And I started doing this last semester when we went online. And the teams, the groups of 3 that really participated in that, I saw some real improvement. I saw some real interaction there that helped students' grades at the end of the semester. If you post yours and nobody else posts theirs, oh well, there's nothing you can do if other people in the team don't cooperate. They get a 0, you get 20 points. That's how that works. Unfortunately, you didn't get a good review of your product. And one of the overarching, I do this for a couple of reasons. One is, engineers are constantly reviewing other people's work. So the more chance you have to do that, that's good for you. When I was an engineer, I spent 30 or 40% of my time not doing work, but just literally reading other people's reports and trying to find mistakes, trying to convince myself that they were right. So you do a lot of that as an engineer. The other thing is that it provides some student interaction. Another thing is it should improve your grade. And then the last thing, the biggest thing, quite frankly, is as humans, we all have a desire to not want to show people our unfinished work. We don't like that. We're like, I'm drawing a picture. Oh, can I see it? No, it's not done yet, right? We all know this. I'm writing a short story. Can I see it? No, it's not done yet. That's our normal human response. This response is harmful to you in a professional environment, I promise you. You want to start out with draft documents and send it to everybody who's got a voice in that document or a concern about that document. And you want to learn to get rid of this I don't want to show it till it's done mentality, and instead go into this, I want to show it while it's a third of the way done or halfway done, and get feedback. And the reason is people's feedback makes you put out a better product. If you're way off the mark early on, why do you want to spend 20 hours of work doing something way off the mark when someone could fix that and save you all that work? So that's the multi-pronged goal of this exercise. But it doesn't work unless you guys, for P3, it doesn't work unless you guys, put up your work like 48 hours ahead of the actual due date so that people actually have time to respond to this thing. Now for the P4, 5, 6, where you're turning in your code, I'm fine if you just turn in your code to me and to that at the discussion group at the same time. If you want to do it early, that's within your group, but turn it into me and to the discussion group at the same time. And again, the idea is you're showing your work. So the way you turn in P4, we'll talk about this in a future discussion, is you literally demonstrate your product to me. You literally demonstrate your code to me. And guess what? At the end of the first sprint, it's not done. But you say, okay, I have these 3 user stories. These are the 3 user stories I tried to complete, and I completed 2 of them. Let me show you my code and show you that those 2 user stories actually work. And what happens is, this is going to be tough this semester, by the way, because there's 93 of you. But what happens is we get like a 5 or 10 minute discussion. And along the way, I get to look at your code and I'm like, oh, okay, but if you did this, your life is going to be a lot easier. Or maybe if you did this, it would solve this problem you're having. So it gives an opportunity for us to have a quick one-on-one where I actually get to give you advice about your code, or if you're having a question, I'm not sure how to do the next part. Oh, okay, let's talk about that for a couple minutes. Now, like I said, there's a lot of you guys, right? So what's happening here is basically from here, 29 March on, I've got some lectures in there, but it's not required material. It's informational only. No tests, no quizzes, none of that stuff. From the 29th of March on, we basically have a lot more free time for this kind of activity. So when you turn in your P4, during class time, I'll actually be asking people for review. And because there's so many of you, I can't fit you all in the 6 hours that we have during the week for lecture. But we'll figure out other times to do that. I have office hours also on Wednesdays that you can come to. Okay. Now let's get back to what's happening right now. Let's play around with the sheepdog game, and let's go here and think about requirements and tests. Let's do a simple requirement. Give me a requirement.
The sheep need to have a certain, the sheep need to know where the dog is, they know when to run away.
Okay, so let's see, I heard at all times, or just when needed?
I would say at all times, just to make
Right
it
away.
simpler.
Yeah, exactly. Right away, we've got a question. Shall have access to the dog X location, Y location, all time. Now notice we're not describing how that happened. The requirements shouldn't lock you into a solution. The requirements should say what you need. And what we need is we need the sheep to know where the dog is. And then we can do that too. Okay. Now, I like these requirements. They're not going to be the best for our discussion, and here's why. I'm asking you to do testable requirements. In industry, you can actually do prove a requirement through your design. And since I have the sheep and terrain inside the sheep, would you say that I have already met these requirements through my design? You can make a strong case for that. Now, you could still test that. You could still test that. You would have what would you check to see if the sheep X, to see if the sheep knows the dog X location, Y location? How might you test that?
Could you make a print statement?
Yes, what would that print statement print?
You'd have to get the dog's location inside of the sheep object.
Right? What's your input? How about we do this? What do I call it? Game controller? I'm covering up my stuff. Game controller. What did we call this? Set dog. Right, so now I've created a dog, I've created a sheep, and the game controller is supposed to pass that dog information down to the sheep. So we're doing that. And then we can say, dog dot set X location 5.0 and dog dot set Y location 5.0. And then what? And then what's my output? And then the output should be, or the expected behavior should be, inside the sheep class, it should be what? Dog dot get X location equals 5.0 dog dot which you would verify with a print statement. Or if you want to do, use the debugging facilities inside of Eclipse. Eclipse also, as I mentioned before, has something called JUnit testing, and you can set this up as a test inside the JUnit testing. And the bad news with that is you have to learn a little bit more to go through the JUnit testing. The good news is once you set this test up, and whenever you change your code, you can automatically run all your tests again. But notice we're using specific values. Now there's a weirdness here because I'm saying your requirement shouldn't say how you solve the problem. They really are talking about functionality. And yet there's a lot of design solution in this test case, right? Well, that's because we're mixing up, we're doing the requirements and the design more or less at the same time with P3. Depending on the kind of development paradigm that you're in, sometimes you develop all the requirements and then you develop all the design and then you develop the test cases. So the test cases do have access to the design. But notice that the requirements did not. But I'm using specific values here, and we're telling the user what to, or I should say the person who's conducting the test, we're telling them what to put into the system. Now, how does the user or the person conducting the test set the dog X location and Y location to 5.0? Can you do that from the keyboard? Can you do that from the gameplay interface? Almost certainly not. So how did those values of 5.0 get in there? How do we know that it's 5.0?
You can set it there as a starting point.
You could. That's one way. But what if I want to run another test at 7.0?
You could also put a kind of use it as a random, like a random number generator to determine where you start off if you want.
Okay. If it's random, how do you know that everybody performed the same test? There's an easier solution. You write methods in your code that are just there to do testing. That's their job. And then you can run test cases. It's your code, right? If you wanted to write a method where the game controller made a dog and made a sheep and gave the dog to the sheep and set the dog X location at 5 and the Y location at 5, could you write a method to do that? Yeah. What might you call that method? Test case number 1. So you're allowed to write code in your code that's only there for testing. You may, and you can make that as simple as you want or as complicated as you want. You can make it as simple as you want by writing having additional methods in your class that are testing methods. And if you look at homework 1, homework 2 for sure, that's exactly what I provided for you. Methods that were there just to run tests. Now, you could also have your code. Every time you make your code, make a copy of your code. This is a little tougher, right? It's a little harder to keep up. Make a copy of your code, put the test methods in the code copy. But as a general rule, there's no good reason to do that, and it's tougher to keep up. And the third way is, you could, if you choose to, you're not required for this class, you could use JUnit testing, because the JUnit basically would take care of this for you. In the JUnit, you build a game controller, you build a sheep, you build a dog, blah blah blah, and then you put in these test values, and then you have pass-fail criteria based on Boolean tests. Sheep.dog.get X location equals 5 and sheep.dog.get X Y location equals 5 would be the Boolean test to pass. So I'm not trying to push JUnit on you, because it is, you do have to learn an additional system. But for those of you that are comfortable with that, be aware that it's available to you. Let me give you a slightly tougher one in 6 minutes. Oops. Now, this is a singular sheep. It is not all the sheep, right? So first of all, is that a good requirement?
It is, because I feel like radius would be a good way to measure it, because the dog can come at it from any side, and it's looking for the radius of it, so.
Okay, good.
Though you may want to be a little bit more specific about like how far into the radius where you want to run away from.
How far within the radius, or?
Like in the radius, like once it gets like, like where, like define how big the radius is.
Yeah. So that's one thing, right? We don't have an activation radius. So remember up front, we had I need more space. The discussion section ahead of the actual requirements. Right, so we're going to have now we know exactly how close the dog has to be to the sheep in order for the sheep to start moving. Is there any other terms that probably need definition there? This is where our real world experience gets us. If you were watching this in the real world, you would know immediately if the dog was moving towards the sheep. But how does the computer with data determine that the dog is moving towards the sheep?
I would say it would use a sort of, we would have to set up like the X and Y location.
Yeah, right.
We would have to use that to determine.
Yeah, there's a lot of geometry involved, a fair amount of geometry involved. So basically, if you said, okay, the distance from the dog to the sheep is, the line between the dog and the sheep is at some angle, then the dog direction must be at plus or minus 45 degrees from that angle. We're going to call that moving toward. You can come up with these definitions. And what does run away mean?
It would have to be like the opposite direction of the dog, but for this one, you probably have to do, again, working with the grid pattern. You'd have to like make it to where like the X and Y location are no longer in the same like area of the dog.
Right. I would do it where if you draw a line between the dog and the sheep, that line has an angle, and I would have the sheep movement be at the same angle. I'd do it that way right off the bat. But you have to define that. Now, technically, I've got two requirements here. One is that the sheep should move, and we don't specify how they move when the dog is within that radius. And the second is that the sheep should move in a specific direction. So there's really two requirements that I could make out of this. One is to test that the sheep moved at all, right? That its speed is non-zero. And then the other is to test that its X speed and Y speed tangent is the correct angle. So I can make two requirements out of this thing. But notice how your natural language usage will bite you in the butt, because you know what running away means. We've seen it. We've all watched Monty Python and the Holy Grail. We know what that looks like. What does it look like in data? What are the numbers that you're going to use to verify it? And that's the kind of thing that until you experience this, it can be difficult to tease out. Oh, and by the way, writing requirements is hard forever. It really is a tough part of software engineering. Okay, we're at time, guys. But think about this stuff. Come up with, if you come up with requirements early, ask your TAs to look at them. You can ask me too, but there's 3 of them, so you get a better shot. If you see anybody in Discord, throw a requirement out there. Ask them to cheat it. Ask them to tear it apart, because what they're doing is improving the requirement. Okay. See you on Monday.
See you on Monday, sir. Have a good weekend.
Thanks. Have a good one too.